Okay, so um, today we're going to talk about, I think, one of the most powerful and like deep and fundamental parts of order of magnitude estimation, which is understanding atomic energy scales and other scales and being able to connect that to the human scale. And so then you can actually answer a lot of questions about the world. So our agenda for today, we're going to learn about the scales of atoms. We're going to do like a kind of practice question on density. We're going to do one on like energy of materials from thinking about atoms. Those are like a practice problem. And then we're going to have one or two cool group problems that actually use some of these things we did earlier. So, and then we'll review the solutions. So this is actually one of my favorite things that Feynman said about, why the things we're going to learn today are so broad and important. And, he said, if in some cataclysm, all of scientific knowledge were to be destroyed and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis or atomic fact that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see there's an enormous amount of information about the world. And so you can actually derive some of these various scales by some arguments, but I'm going to just kind of give you these like main things kind of as keystone facts that we'll build upon. And if you want to know how they're derived, I would recommend looking at Sanjoy Marahan's like order of magnitude estimation textbook, where he goes into this in more depth. But I think like that's not exactly what we want. So the first thing that we kind of want to figure out, or a kind of base quantity that if we know it, we can build a lot of other things up from it, is the size of atoms. So just to remind you, atoms are consisting of a nucleus, which is positively charged, and some electrons that, because of quantum mechanics and stuff, make a shell around the atom. And for various reasons, only 2 electrons can go into the first shell, and it's kind of spherical. And then that's all that can fit in there. And then that's like a certain energy level of the electrons. And then there's another spherical shell. And then there's like 3 kind of oblong shells. And so the kind of first energy shell has 2 electrons. And the next one has 8, 2 plus 2 plus 2 plus 2. So that's like something to remember. So what are the size of atoms? The length scale of atoms is angstroms, which is 10 to the minus 10 meters, or a tenth of a nanometer. Like that is the like proper scale for things that are happening like in the atomic or molecular world. And so there's an interesting kind of little fact that the size of atoms is actually related to how many like shells are filled. So for n less than or equal to 3, you can use this mnemonic that the size of an atom is n times an angstrom. So a hydrogen or something with only 1 shell is 1 angstrom in size. The atoms that have like 2 shells filled, which are kind of your next level, I guess your like carbons and oxygens and stuff, are 2 angstroms in size. And then anything, and then 3 or greater is actually all around size 3 angstroms. If it's higher shells are filled, the nucleus is actually attracting more and kind of pulls things inward and makes them smaller. So for all other atoms, they're about size 3 angstroms. And so like, we're just gonna like, for now, we're just gonna remember that most atoms are 3 angstroms in size. So the first question I want you guys to figure out is, assuming an atom is 3 angstroms in size, how many atoms are in a cubic centimeter? How many atoms could I pack into a cubic centimeter if they're each 3 angstroms in size about. So I think I will pause the recording. Alrighty, well, I saw in the chat that a fair number of people realized that like we should probably be getting something around Avogadro's number, because that's kind of a human scale, number for a number of atoms. But instead of having to memorize Avogadro's number, we can kind of derive it, which is kind of cool. So to go through, we can imagine that each atom is like a little cube of 3 angstroms in size that we're stacking together. And so a 3 angstrom cube, 3 times 10 to the minus 10, becomes 27 times 10 to the minus 30. And 27 is about 30. So I'm going to make that 3 times 10 to the minus 29 instead of 3 times 10 to the minus 30, or 30 times 10 to the minus 30. So 3 times 10 to the minus 29 meters cubed per atom. So that's how big kind of each atom is. And then, we wanted a cubic centimeter. So how many cubic centimeters are in a meter? 1 cubic centimeter is 10 to the minus 6 meters. So there's 1,000,000 cubic centimeters in a meter. So so it's like this many meters per atom, but then we can flip this around and we can make it kind of like 1/3 times 10 to the 29 atoms per meter. And per meter cubed, but then we want 1,000,000th smaller than that. And so we get something on the order of, 10 to the 23 atoms per cubic centimeter, which is, about 6 times 10 to the 23 for Avogadro's number. So, right there, from knowing that little fact about the size of atoms, you can kind of get within the realm of Avogadro's number. And then if you also know like the mass of an atom, which we won't do here, but you can do something similar and you can figure out densities of various materials. And so, it turns out that most material densities are between 1 to 10 grams per cubic centimeter. So we're getting like all these facts about materials in the world, how much things weigh, all from just, knowing that things are made of atoms and about how big atoms are. So the next thing, so David White asked, does packing arrangement matter? And, there are various ways of packing spheres together, more dense or less dense. And, like if we were going for exact numbers, that would probably matter, but we're just doing order of magnitude here. And so I think the packing fraction difference is within, it's some small correction. It's like a 20% kind of thing. Yeah. So next thing, the atomic energy scale. So today we learned that atoms are like on like an angstrom size. So that's like one thing you should just memorize. That's like a keystone fact that we can put in the Discord. Another keystone fact is that the energy scale of like atomic bonds or molecular bonds, things where electrons are being held to atoms or shared between atoms, is on the EV scale. So the other like big fact that you should remember is that an EV is about 10 to the minus 19 joules. It's the actual scale is a little bit more for covalent bonds between carbons or oxygens or hydrogens. Those bonds are about 4 EV. So to break each one takes about 4 EV of energy. And the what is it called? The binding energy of a hydrogen to like fully pop off an electron from a hydrogen is about 13 EV. So when you have these molecules bonded together, it's not necessarily like an electron purely bonded to hydrogen is actually stuck a little harder than the electrons that are kind of orbiting around in molecules. but this is kind of roughly the right energy scale. And so I would recommend you guys write down this 1 EV is about 10 to the minus 19 joules for our next question. So our next question is, how many joules per mole? If I know I've got some material and I'm estimating that I've got about 1 EV of energy per molecule, how many joules per mole is 1 EV per molecule? So that's kind of our next question. And this is going to get us going from the, again, the atomic scale to the human scale. If I know something about, what type of bonds are in my material, that will, let me figure out total energy stored in there, or, later in maybe future classes, we'll learn about surface tensions or other things. So you'll be able to figure out a lot of material properties from knowing kind of energy scale of molecules to human scale. So this is our next question. So I'll stop the recording. Alrighty, so this one, how do we do it? We first say, okay, well, 1 EV per molecule is actually 1.6 times 10 to the minus 19 joules per molecule. And then we know that from Avogadro's number, 6 times 10 to the 23 molecules per mole. And so we then multiply these together. We say 6 times 1.6 is about 10. We say 10 to the minus 19 times 10 to the 23 is about 10 to the 4. And that extra 10 makes it 10 to the 5. So we get 10 to the 5 joules per mole, or 100 kilojoules per mole. So 1 EV per molecule is about 100 kilojoules per mole. This seems a little abstract, like, okay, that, I don't really know exactly what that means. So I thought I would show you guys how this applies to TNT, or trinitrotoluene, and how we can estimate like how much energy is released by a ton of TNT by using kind of this way of looking at energy in molecules. So I did the order of magnitude here, but and it turned out I wasn't quite right, but I was within an order of magnitude. So as usual, we're being sloppy. We're definitely ignoring important things, or just blurring over details. But it's still nice that we at least get within the right ballpark. So the way I thought about this problem, I did look up like what trinitrotoluene looks like and its molar mass. So we probably could have estimated that, but we got to start somewhere. So here's the molecule, and what I was thinking was that the way when trinitrotoluene burns, like a lot of these carbon-carbon and carbon-nitrogen bonds are going to be broken. So trinitrotoluene is a toluene, which is this carbon, ring, and maybe this thing on top. And there's 3 trinitros. So these are like nitro groups of like a, nitrogen and some hydrogens. So I was thinking, okay, well, how many of these like big bonds are we going to break? And actually, if we think about it, what's going to happen is these nitrogens are going to bond to nitrogen. They're going to make N2. The carbons are probably going to form CO2 or something, and there's going to be some water forming because when hydrocarbons burn, they make CO2 and water. So I was like, okay, well, the main things that these carbon-oxygen bonds are probably going to reform and stuff. These hydrogen bonds, let's not worry about them. Let's, for the most part, just count like how many carbon bonds are breaking and how many carbon-nitrogen bonds are breaking. So as we learned before, the scale of these kind of bonds is about 4 EV. And so I counted like 6, 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10. And so I said, okay, when a molecule of trinitrotoluene like burns or is combusted, it's going to release about 40 EV per molecule. And that was actually too high, but that was kind of my guess. And so then as we just learned, 1 EV per molecule is about 100 kilojoules per mole. So 40 EV per molecule would be about 4 megajoules per mole. And then if we know that TNT is 227 grams per mole, 400 kilojoules per mole divided by 200, 1 mole per 200 grams gets about 20 kilojoules per gram. And the real answer is about 4 kilojoules per gram. So I was off by a factor of 5, but we do get in the right order of magnitude. And interestingly, TNT is actually defined like the energy equivalent of a TNT is actually defined to be 1 kilocalorie per gram. So it's like a little bit more than 4 kilojoules per gram. But then you just scale that up from grams to tons to figure out how much energy is a ton of TNT. But I would recommend writing down like 4 kilojoules per gram, because we eventually, if we have time, will want to use tons of TNT as an energy equivalent. So that is kind of the stuff I wanted to talk about for today.